Hello everyone, my name is Nisha and today I am presenting our mini project. The title of my project is Liver Tumor Detection in Abdominal Ultrasound. In this project, I will discuss introduction, liver condition types, liver tumor detection techniques, literature review, dataset, GLCM and CNN features, architecture and flowchart, experimental results, conclusion and references. So in introduction, we all know that liver is the most important organ responsible for metabolism and detoxification. And liver tumor, what is liver tumor? Means an abnormal growth in liver cells. So for that, early detection is desired. Abdominal ultrasound imaging is commonly used for detecting liver abnormalities. Why ultrasound imaging? Because it is non-invasive, safe and cost effective. These are the example of liver tumor detections. And liver condition, the first type of the tumor is benign tumor and the second one is malignant. Benign generally non-cancerous and it do not spread in other tissues or other body parts, but malignant is so dangerous. It can spread in other tissues or body parts. So for that, early detection is desired. These are the examples of liver condition types. The first one is an image of a normal liver. The second one is benign tumor liver, and the third one is malignant tumor liver. These are the techniques which we use for the liver tumor detections. In this project, we have used ultrasound imaging, but some of other techniques can be used for this detection. Image processing technique, deep learning techniques, biopsy techniques, MRI, computed tomography. These are the literature reviews. In this literature reviews, we studied different research papers related to liver tumor detection. The previous studies used methods such as GLCM feature and SPM classifier in ultrasound images. Then CNN based deep learning and hybrid SVM approaches. This recent research shows that deep learning models provide better accuracy and robustness in ultrasound image classifications. So these are the dataset. We have used ultrasound liver images dataset, which is present on the Kaggle. Means we have used this dataset from Kaggle. This dataset contains a total of 735 abdominal ultrasound images. So from these images, we divided these images in two parts. The first one we used for training set, and for second we use for validation set. So the 75% of these ultrasound images we use to train our model, and the 25% of these images we use for the validation. Okay, these are the overall distribution, dataset distribution. Means 59.2% of the overall dataset are malignant, and 27.2% are benign, and 13.6% are normal. This is the dataset distribution which we have used for training and validation. It means the 300 plus images we have used to train our model for malignant, and almost 100 images for the validation. Same for benign and normal. These are the examples of some liver images train set: malignant, normal, benign. These are some images shown. So what is GLCM features? GLCM means gray level coherence matrix. It is a texture-based feature extraction techniques. In it extract handcrafted statistical texture features from ultrasound images. GLCM feature includes contrast, correlation, energy, homogeneity, entropy. Computationally, it is less expensive compared to deep learning models. So these can be used. These are the comparison table of GLCM feature and CNN features. It means these there are some differences. It means handcrafted feature extraction in GLCM. CNN, what CNN do? Automatic feature extraction. This is texture based analysis. This is deep hierarchical learning. It requires feature engineering, no manual feature engineering. This is less computational cost, high computational cost, easier to interpret, more complex to interpret. It can take lower training time, higher training time. So these are the differences between GLCM and CNN features. So these are the main part of our model. Means this is the flow chart of our model. So first of all we collect data, then we process our data. Before we process, we need pre-processing, because we know that raw ultrasound images usually contain speckle noise, low contrast and unwanted variation. Therefore, pre-processing is very important before model training. So we include some noise reduction, contrast enhancement, image normalization, removal of unwanted artifacts. Okay, the third step is resizing. We resize our images, all images in a same matrix. In our model we have used 128 cross 128 matrix size for our image. Then we do data augmentation, and then encoding means example 1004 normal, 010 for benign and 0014 for malignant. The processed images are then passed into the CNN based hybrid deep learning model. During training, the model learns pattern from ultrasound images. The final layer is the softmax layer. It converts output into probability values for each class. So finally, the model classifies the liver images into normal, benign and malignant. This is the block diagram of architecture of CNN-based liver condition detection system models. This model consists of a convolution layers, max pooling layer and flattened layers, dense layer, dropout layer and a softmax output layer. This is the block diagram of architecture of efficient net B0. Same in this convolution layer, MB convolution layer, and these layers are used. Efficient net B0 is a transfer learning model pre-trained on ImageNet dataset. It provides better feature extraction capability and improved classification performance. This is the comparison table between CNN based architecture versus EfficientNet B0. These are the comparisons, different for the main is for overall performance. The CNN perform moderately and EfficientNet B0 is a superior. And we can see tumor boundary detection in CNN model. This is weak and this is strong for the case of EfficientNet B0. Small dataset performance, this is poor and this is good. Okay, validation performance, this is unstable and this is stable. These are the comparison matrices for accuracy, precision, recall, specificity, I, OU, FPR, FNR, DSC. Here TP means true positive, TN means true negative, FP means false positive and FN means false negative. These are the results we get from our model. This is the graph for training accuracy and this is for validation accuracy. If we increase the number of epoch, we get a better results. Same for loss This is a graph of training loss and this for the validation loss. Same for epoch. If we increase the number of epochs, we get a fewer loss in our results. This is for precision and this is for recall. These are the confusion matrix. Confusion matrix is a matrix plotted between true values and predicted values. These are normal for malignant, these are for benign. So these two represents. This is we get from when we use CNN based models. So there are some mismatching for the benign. So we use FSCM net P0 model. Then we get a large number of images which matches with the true or actual images. These are the conclusions. Final conclusion. It means in liver tumor detection using ultrasound imaging, deep learning technique is very useful for early diagnosis. The CNN model achieved moderate performance while FCNet B0 provided a higher accuracy, precision, recall and robustness against ultrasound noises. These are the credit author. My contribution in this project mainly involved reviewing research literature, understanding previous liver tumor detection methods, collecting the ultrasound dataset from Kaggle, and preparing the presentation and documentation. My project partner worked on model preparation, code implementation, training of the CNN and efficient V0 models. These are the references used in this project, including research papers and review articles related to liver tumor detection and deep learning techniques. So, thank you for your attention. I hope this presentation clearly explained our work on liver tumor detection using ultrasound imaging and deep learning techniques. Thank you.